In the last video, we looked at this particular function here and found its critical points. In this case, there was only one. And we plotted this function, and we can see that it has, as in a previous video, shows some sort of saddle point. Okay. And so in this video, I just want to kind of motivate the second derivative test, and we'll get the general result called the second derivative test. Here you can see that I'm trying to take the gradient. And if you look at the gradient of this entry and then the gradient of this entry, we will get something called the Hessian, or the matrix of second partial derivatives. And you can compute that in Mathematica by taking the derivative with respect to both x and y. And we're going to take two derivatives of it. And this is what we get for, matrix form, for the Hessian. So the partial with respect to this entry with respect to x is 14, the partial with respect to y is 5, and the partial with respect to x is equal to 5, partial with respect to y is equal to 0. So that's where the Hessian comes from. And now we've learned in previous videos that the Hessian becomes important when you want to compute the second directional derivative. So if you pick any vector that you want, put the same vector twice, we can compute how the function is curving in that direction mn. So if you want to pick the vector to be 1, 1, and we want to see if that vector, the curve in that direction, is curving up or down, you would compute the second directional derivative. And we can see that that function is curving down, minus sign, in the 1, 1 direction. So this function, if you look at our point of interest, which was the critical point somewhere in the middle here, 1.2, 2 point something, and then you look at the value, the direction 1, 1, the function would be kind of sloping downward in that direction. The curve on the surface would be like a little parabola facing downward. Okay. If you change that to be change the direction and put the same direction vector in both places and compute the second directional derivative in this new direction, notice that you get a number and it happens to be positive. And this is saying that in another direction, the curve on the surface is going to be a parabola that is kind of turning upward. Okay? So it is this second derivative in any direction that is going to lead us to the second derivative test. And so let's focus on that idea now. Okay, so you'll recall that from Calculus 1, okay, you had a function of one variable, y is equal to f of x. Once you found a critical value, or a critical point, that was a place where the derivative at a certain value, x is equal to c, gave 0 for the derivative, or the derivative evaluated at c does not exist. Once you found that value of x, you can then single out that value of x to test if what's going on with the second derivative at that point. And the whole point of the second derivative test from Calc 1 was to determine if the second derivative was positive or negative or 0. Okay. If the second derivative came out to be positive, we knew that whatever this function was doing at the value of c, that the second derivative, that the function had to have a quadratic approximation that was facing upward. So maybe the function looked something like that little pink smiley face facing upward at that point. If the second derivative came out to be negative at the value of c, you knew that the function had to be turning downward or being curving downward at c, and therefore your function, whatever it was doing at this point, had to look something like a parabola that was turning downward. Okay? And 0, the derivative being equal to 0, was an inconclusive case. Okay, so that's exactly what we need to do for Calculus 3, that we need to look at the second derivative. And the equivalent of the second derivative is equal to the Hessian. Okay? And the Hessian is equal to the matrix of second partial derivatives. Okay? And then what we want to do is we want to see what happens in Calculus 3, that we don't just have a one-dimensional curve, but we have a surface. Right? And therefore, we would like to be able to look at what is happening, how is the curve curving in any possible direction that you pick. Okay. If whatever direction you pick, I like to call it in this case mn, where m and n are whatever values you want them to be to make a direction vector, then you would look at the Hessian in that direction. Okay. And we would want to check the sign of it. Okay, so what we're going to do is we are going to test the Hessian, okay, dotted with mn, dotted with mn. So we're going to look at the second directional derivative of this function in any possible direction. And then we're going to try to say that if that second directional derivative is positive, then what we know there is that the function was going to have a quadratic approximation that was always, maybe that's what your surface looked like. It looked like a little paraboloid that was opening upward. So the surface would be well approximated by that quadratic approximation. If the function, the second directional derivative, comes out negative in any direction, right, no matter what that direction is, then you know that the quadratic approximation of your function was going to be like a paraboloid facing downward. And so maybe your surface was doing something like this at that point, and this is the quadratic approximation of it. And there is a case for that we need to watch out for, that sometimes there is a saddle point. Sometimes the function faces upward, and sometimes the function is turning downward. So we also need to watch out for this case in Calculus 3 for the function opening upward and downward. Okay. So let me see. Let me copy this page. And then we'll move on with the analytic part for computing. Oh, sorry. Sorry, I'm trying to just copy this page. Copy pages. Okay. So let's go to this page now and clear it, and we'll work out exactly what we were trying to do. So as promised, I'm trying to compute the Hessian in any possible direction. And I would like to look and see if that is equal to positive, negative, 0, or something else, or we'd like to analyze this case. Okay. Now when you look at the Hessian, fxx, fxy, fyx, fyy, multiplied by mn, multiplied by the vector mn, so do the second directional derivative. According to this formula, when you multiply that out, you'll get m squared, whatever the number m is, fxx plus 2mn fxy plus n squared fyy. And this formula is rather hard to analyze. This is hard to analyze because we're trying to figure out if it's positive or negative. And now we know that m squared is a positive number. We know that n squared is a positive number. Even if m was negative and n was negative, when you square it, you make them positive. But we don't know about m times n. If m was positive and n was positive, then the whole thing would have been positive. But if m was negative and n was positive, then the answer would have been negative. And then we wouldn't know what would have happened to a positive minus a negative plus a positive. We wouldn't have known what that answer came out to be equal to. It depends on how big those positive and negative numbers are. So this formula is really hard to analyze to figure out if it's just positive or negative. So the goal here is to rearrange this formula, and I have a second formula up here that is equivalent to m squared fxx plus 2mn fxy. And I think I asked I can't remember how I came up. Actually, I know how I came up with this formula. What we did is we tried to complete the square. Okay. Plus a second term n squared fxx fxy minus fxy squared divided by fxx. Okay. Now these are equivalent to each other. And it turns out from completing the square. So if you took 1/2 of this entry, added it in, and squared it, subtracted it, you would have been able to factor this expression. And this expression actually is analyzable. And the nice thing is that look how complicated this particular piece is right here. Whatever this is, it is being squared. So that whole result right there is positive. Okay? This n squared is a positive value. Okay? So what we can say is that the Hessian in any direction, mn multiplied by mn, right? It actually won't matter what m and n are. What matters for this being positive or negative or something else completely depends on the function itself. If fxx, the second derivative, is positive, then you'll have a positive number here. A positive times positive is positive. N squared is positive, and if fxx is positive, okay, then this whole quantity will be positive if also fxx and fxy minus this is an fyy. fxx, fyy minus fxy squared, if this thing is also positive. So if the second derivative of the function with respect to x is positive, and this particular combination of the second partial derivatives is positive, then the whole second derivative in any direction is a positive number. Okay? And the second derivative in any direction would be positive then. And then you would know that the function is going to look like a paraboloid opening upward, in which case you would have a local minimum of the function. To get this second directional derivative to be negative, right? If fxx comes out to be a negative number, this term will be negative. This term we already know is positive. A negative times a positive is negative. And if n squared is positive, if fxx is negative, then we can make this whole term negative, which will make both terms negative and make the whole second directional derivative come out to be negative. So long as fxx comes out to be negative and this term fyy minus fxy squared is also positive, then we will have the second directional derivative in any direction coming out to be negative, and the function will look like a paraboloid opening down. Okay. There is another case, and a little terminology will be helpful here. The quantity, let me write this in a different color. This quantity appears often enough, this particular combination of second partial derivatives. This is called D for discriminant. If D, in both of these cases, it needs to be positive to get a local maximum or a local minimum. But if D should come out to be negative, a negative number, if D will come out to be a negative number, then that's going to imply that we have some sort of saddle point. Okay, and examples will bear this problem out. Okay. So that is an analysis of where the second derivative test will come from. It's not just whether or not one of the partial derivatives is positive or negative, but it relies on a particular combination of partial derivatives. And that's what we can see here in the chart from the textbook, right? And it just comes down to an analysis of this equation. If f(x)(x) is positive and D is positive, then we know that the function is going to look like a paraboloid opening upward, and that is when you can say that the function has a local minimum. But if the second derivative comes out to be negative and D is also a positive number, then we have a local maximum because we know that the paraboloid, the function, is probably going to be well approximated by a paraboloid that is opening downward. And then there is the case where D is simply a negative number, and that's called a saddle point. And if for some reason D should come out to be equal to 0, then you need to keep thinking and find other methods to determine if the function has a maximum or a minimum because the test is inconclusive. So that is an outline for the second derivative test, what you have to do to compute it. Following videos, we will look at some examples.